with another edition of Ask an Astronomer. Happy equinox. We are here with our trusted and favorite astronomer, and that is our astronomer Marley. Hey Marley, how's it going?
It's good. Glad that it's fall and not 30 degrees anymore, but not excited for the rain that will eventually come.
Yes, and here on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh, we have that special brand of rain that mixes with all the leaves, and then it's just sort of like a big wet mush.
Sludge.
Well, besides that, what's your favorite? What's the favorite part for an astronomer as we get into the fall season?
I don't know, because typically with fall brings lots of clouds, which makes it hard to observe, which is never fun, right? So I'd have to think about any benefits, honestly, in terms of astronomy. Though when the weather does get colder, the air gets a bit better. If you do get a clear night,
Okay.
for observing, the air is has to do with like pressure and stuff like that. So when it's colder, you get better air quality, which makes for less turbulence and makes your images look a bit better, which is always nice.
Yeah, and so we're actually going to be viewing tonight. We have a special event here on site for Equinox. We are going to be viewing actually a Canadian premiere of a fabulous documentary called Star Stuff. And we're going to be chatting live with the director, Malad Tankshir, who lives in Italy. And then afterwards, we're going to go to the observatory and we'll have a chance to look at a couple of planets that are going to be out. And it's looking like a clear evening. So if you're here near us, come on by, watch this documentary. It's going to be really fun. And we're also doing something new for this show. We usually go to YouTube, and if you're there watching on YouTube, hello, tell us your favorite thing about the fall season. We also go to Tell Us Optic. Hello to you folks. And we're also live on Facebook for the very first time. So drop a hello if you're watching on Facebook and let us know what your favorite thing about fall. And just like Marley said, love and look at those planets with that crisp sky. And you know what else loves looking at the planets? That's the new JWST, which has turned its eye towards our solar system. And that's the theme of this show, some really fabulous and incredible pictures. Let's get into today's topic. And of course, if you're out there watching, if you have any questions, drop them into the comments. If you have any questions about anything else besides what we're talking about, we'll answer them too. We'll go for the next 20 minutes. But let's have a look at these fabulous pictures, Marlon.
Right. So recently I've been noticing a lot of web looking at the solar system, which is great. But with that comes a lot of questions of why is it looking at the solar system? It is often marketed as this telescope that's supposed to peer into the very beginnings of the universe and the very earliest star systems and planetary systems, which is true. But also part of its mission is to look at our solar system. So if we take a look back at Webb's science goals, we have four main ones, right? First light and reionization, which is like what are the first galaxies and stars? When did the light first form? The assembly of galaxies, how do they get their shape? How do black holes influence them? Birth of stars and protoplanetary systems, which is understanding the birth and evolution of stars and their systems, how they change over time and how they form. And then we finally have this fourth one, which is planetary systems and origins of life. And that one science goal gets hijacked by the atmospheres of exoplanets, right? That is like kind of Webb's big thing. It looked at the atmosphere of an exoplanet recently, and even one of its first images was a spectrum of the atmosphere of an exoplanet. And so that hijacks this category big time. That's something that scientists are very interested in. But a part of that category is study objects within our own solar system. So this is also something that is part of Webb's science mission. And why Webb for solar system science, right? If we've built this telescope with all these capabilities to look so far, why bother using it for solar system science? And it's because many different molecules, ices, and minerals have strong features in the infrared. So your water, your methane, your carbon dioxide are all very strongly represented in the infrared. They have very noticeable and strong features in this type of light. Webb is also sensitive enough to gather data on Kuiper belt objects, not necessarily photos or images, but also spectra and different analysis on Kuiper belt objects, which are things we don't really understand and haven't really had the capabilities to look at yet. And so having Webb for this helps. And also, why not? Like if we have this telescope that works so well, why not just look at things within our own solar system with it? It's fun.
Yeah.
So there's lots of reasons why Webb could be used for this.
Well, I've got a couple questions. First off, you label those four categories, the four goals. I'm wondering, when you say hijack, does that actually mean hijack? Like, are there scientists that are vying for a certain percentage of time if they say, we are going to be using the JWST for the planetary systems category, but then within that, there's a whole bunch of other categories that take place? Is that how it works when scientists are vying for time?
Yeah. So when it comes to writing a proposal, you have to state like your goals and like kind of where it fits in.
Yeah.
And so there's lots of different Webb observing goals. And actually, the Space Telescope Science Institute, if you go to the Webb thing specifically for it, they have, approved programs and all these different things that have come through. So there's like general observing programs, which is like things that are proposed by the community and selected by peer review. You have the early release programs, which were the ones that were executed within the first 5 months of science operations. You have guaranteed time, and all of those different programs just allot different amounts of time to different people. But within it, you also have to specify what you'll be looking at and where it fits into the science goals. And so you can say, I'm doing planetary systems and origins of life, but that doesn't really mean anything. It's like, okay, but what system are you looking at? What is it? And often, getting telescope time, heard through the grapevine that it's a bit it gives you a leg up if you mention exoplanets in it, because people really like that. It's very scientifically interesting. But there's also lots of other scientifically interesting things. But it is kind of you got to word your proposals well, because it goes to like a board of people and people have to pick and choose, which one is guaranteed the time, right? So it is kind of a battle almost in a way.
So this is now, these are things that they might not necessarily teach you when you're in school, that not only do you have to be like really good at understanding the science, but you got to be really good at writing proposals.
Yeah, no, that's a huge skill. It is not easy. Yeah. Telescope proposals are very difficult, I find, to write anyway.
So the other thing, so on your next slide, you talked about the Kuiper Belt, and I'm wondering, is the New Horizons team going to be vying for time the JWST, because they're out there in that Kuiper Belt zone, and I think they might be looking for a new object. I'm not entirely sure. The mission is still going, right?
The mission's still going. New Horizons is still going. It's like left its, Pluto system, and it's still out there. And it's funny you mentioned that, Michael. I'm going to stop sharing my slide right now and share a different screen, because as I was looking at the Space Telescope Science Institute's website, you can actually go in and see proposal schedules for what we'll be looking at next. And I was like, I want to know what it's looking at. So if we're looking at this here, this is all of the proposals, or what it's going to be looking at, like approved proposals for the 21st till the 25th of September. And you have, visit ID keywords, whatever. This is all stuff that you don't necessarily doesn't mean anything to people here. But in category, you have all these different, what is it looking at? You see calibration, star, solar system. And if you look over, you see Pluto and Charon. So it is going to be looking at Pluto and Charon. And you can see it's taking a dark for near spec. That will be for helping with data analysis, and also near spec spectroscopy. So it will be doing looking at Pluto and Charon in the spectra. And if you go further down, you will see solar system again, where they're doing another analysis of Pluto and Charon, or looking at it anyways with Webb. So amongst all of these stars and galaxies and clusters of galaxies, we are going to get a view of Pluto, whether or not, because that goes right to the science team that requested the time. Whether or not that gets released to the public, I don't know. But with the trend of everything being kind of solar system focused getting released to the public, I do think we can hope to, cautiously optimistic of seeing some Pluto and Charon images sometime soon.
This is why we have you here on the team, Marley. You are a detective, always looking at all of the fine details. You can't get this stuff anywhere else. This is the only place you can get this, is at Ask an Astronomer. Really exciting stuff. Let's look at these fabulous pictures, though, of our solar system. A very different view that we normally see of some of these very familiar planets.
Yeah, so I wanted to start with Jupiter, because these were kind of the first images that came out with Webb. These are from its commissioning report. So when they were like, I don't know, it feels like 100 years ago, when they were looking at, is it even working type stuff. So it looked at Jupiter to test for performance for tracking moving targets, right? So this is very, everything is moving in space. Webb is moving. Its observing targets are typically, if it's looking at planets or asteroids, are also moving. And so they wanted to make sure that they are able to track it, and to within a certain speed is what they wanted, to be able to track it. They are. It's good. But it was also expected to be challenging due to light being scattered by a bright planet, right? Jupiter is very, very bright. Webb is built to detect very, very faint things. And so Jupiter, being as large as it is very bright for Webb. So, and combine that with like all of its moons, the different satellites that orbit it, there's a lot of light coming off of the planet. And the scattering of that light can affect the fine guidance sensor, right? Which is what Webb uses, built by the Canadian Space Agency. And the fine guidance sensor looks at distant stars, what they call guide stars, to tell Webb where it is in space. And if you get a really bright object, it can wash out the fine guidance sensor. And so it won't be able to know where it is, and it can cause problems. And so these images of Jupiter were taken kind of to verify that not only NIRCam was working and MIR and stuff like that, but also checking that the fine guidance sensor will still work with something so bright near the field of view. And it does. The commissioning report said that it verified that finding the guide star works as long as Jupiter is a certain distance away from the fine guidance sensor. The scientific instruments, so MIRI, NIRCam, NIRSPEC, they were also all affected, and they were contaminated by scattered light, even when Jupiter wasn't in the primary field of view. So that told scientists and engineers that that's something they have to consider if they're going to be looking at a target like this. So these aren't scientific images, right? They're just calibration images. And you can see Jupiter's ring standing out in some of them, and as well as its moons and many different things happening. But they're not they're not scientific. They were just done for calibration.
Yeah, this is interesting. We are actually going to have another event on October 6th, actually, that's going to be all on the Jupiter system and all of the moons that surround it. And they keep finding new moons. And we're actually going to be having a person on the team out at UBC that discovered a whole bunch of new moons. So I'm wondering if anyone there is going to be vying for time with the JWST. But you bring up an interesting point that Jupiter is really bright, but it might be able to detect some of those fainter objects. But would it maybe use the same type of technique? And I don't know if JWST is set up for this, where you can block out the bright light and just sort of look at what's surrounding it, how you might be able to detect an exoplanet with direct imaging.
A coronagraph, that's what that is. So that's the thing that it blocks out the bright light. I'm drawing a blank as to whether or not Webb has one. I don't think it does. But it might. It would be smart if they had it on. I think it might be there, but I don't know for sure. I'm going with cautious no on this part. They have different methods of avoiding light, like they did with Mars, which I'll show later. But this is a scientific image of Jupiter now that Webb took. It's a composite of 3 different filters. So at different wavelengths of infrared lights. Some are in red, yellow, green, and the cyan, I don't know, the blue. And its alignment was difficult due to the planet's rotation. But in this image, this one image we see of Jupiter, you can see the aurora extending to high altitudes. Those are like in these redder parts. We see aurora extending to high altitude above the northern and southern poles. And the great red spot appears white instead of red. And it is red visible. It is white in the infrared because it's reflecting a lot of sunlight, and the brightness is indicated at high altitude. So things that are at higher altitudes will appear a brighter white. Things at lower altitudes will appear like a darker color. So what this means that the great red spot has what's called like high altitude clouds at the very top of it. And so does this equatorial region here. This one band of clouds over here are at a very high altitude. In the other view of Jupiter we got from Webb, we see this wide field view where you can see the rings, very, very faint rings Jupiter has, nothing like Saturn, and two very small moons, Amalthea and Adrastea. Adrastea? I don't know. I've honestly never heard of these moons before. So these 2 are there, and the diffraction spike from Io. So Io is actually out of the frame here, but it's the light being diffracted is making its way into the image. Oh, wow. Same with the aurora. You get these little spikes of light. That's just a residual of like how Webb is built and how light gets bounced around. So it's very bright for Webb for these diffractions to occur. And these fuzzy spots are most likely background galaxies that seem to, photobomb anything that Webb takes because it's just so sensitive to stuff.
Right. Well, this is really interesting because if you look at Jupiter with a normal telescope, like we will be tonight, you can see the 4 Galilean moons, Io being one of them. But this view obviously is even sort of like closer, even tighter, where this ring set is and where these smaller moons are. This certainly is a very unique view that we have not seen of Jupiter before.
No, it's very cool. Even like the colors, right? Like this is not what Jupiter would look like to our eyes. These colors have been like assigned, for it to be able to understand the image. And I think there's another, I can't really see it, but there's Io's footprint, which is like at the bottom here, which is like the shadow of Io being casted on the moon on Jupiter. But you can't really see it too well in the picture. Very cool. The other thing that Webb is taking a photo of is Mars. So a note off the top is that this science is in progress, right? They released these images, but the science is still going under the peer review process. It hasn't been peer reviewed yet. It hasn't been published yet. Once the paper is finished, because the team is writing a paper about what they found, it'll be submitted for peer review and published eventually in a journal. So this is all still science that's kind of up in the air, hasn't been really gone through the scientific process just yet in terms of peer review. But this is Mars in the view of Webb. And no, Webb does not take photos in color. They assigned this reddish orange, so it very much looks like the surface of Mars. It is the surface of Mars, but what it is showing is darker and brighter regions. They just assigned it the colors that Mars typically looks like, but that's not a optical image of the surface. And you also have a heat map of Mars as well. And what's interesting about this heat map is it's showing the thermal emission as a planet loses heat, right? So planets will lose heat, radiate heat away. And the bright spot here is from the sun being nearly directly overhead at Mars. So that's why this one spot looks so bright. And the poles receive less sunlight, as you can tell, like the North Pole looks a lot cooler or darker. And if we were to draw the equator through here, you'd notice that the Northern Hemisphere is receiving less sunlight overall because it's currently going through winter, which is very cool. The Hellas Basin, which I first noticed because I was like, what is this weird speck doing here? This is not a marker of Hellas Basin being cooler or anything. It actually has to do with the air pressure happening. So Hellas Basin is actually at a lower altitude and so has a higher air pressure. And a higher air pressure will like suppress the thermal emission at the wavelength due to a scientific artifact called pressure broadening. But all this to say is Hellas Basin is not randomly cooler than the rest of the part where it is. It's still warm because as light is emitted by the planet, it goes through the atmosphere and some of it gets absorbed by carbon dioxide molecules and things like that. So at a lower altitude, you're going to have a bit of a thicker atmosphere, more absorption going on. So you're getting less of that, seeing less of that light, but it's not receiving less sunlight or anything like that.
Right. And when you do say warmer in context, like Mars, even in the sunlight, is still pretty cold, right?
Oh, yeah. No, it's still cold. Yeah, it's not like a balmy 30. It's pretty chilly still. Yeah.
But it is going through seasons and it is certainly in winter. A very cool, very unique image of Mars. What else do you got?
I've got my favorite thing ever, a spectra. This is a spectra of Mars's atmosphere and its composition, which is very cool. So they, looked at how the light is interacting with objects in Mars's atmosphere. And the spectrum is actually dominated by reflected sunlight at wavelengths very short, at the shorter wavelengths of light, and then at thermal emission at the longer wavelengths. And so what this is showing is the white line is the data that they collected, and the purple is their best fit model to explain what is going on. And so we have these dips in it, these absorption features where we have carbon dioxide, and then a small water one and more carbon dioxide, more carbon, Mars's atmosphere is mostly carbon dioxide, but also we have a carbon monoxide feature going on here. So this shows where the light is being absorbed by different molecules in Mars's atmosphere. And why would they do this with Mars? Because the imaging and the spectroscopic data put together can be used to explore regional differences across the planet, right? In areas where we are seeing dimmer areas, looking at the atmosphere composition there, can tell us, what's going on with the regional differences of Mars. And we can also look for trace gases in the atmosphere, including methane and hydrogen chloride. And so if we find an interesting feature in the atmospheric composition, we can then look at the surface of the planet to see where that may be coming from, if there's an active volcano or something causing that type of emission.
And this is the kind of work that initially was done, on Mars when the Viking lander landed, looking for trace elements of methane, but we've certainly come a long way in understanding what's going on with Mars's atmosphere since then, right?
Oh yeah, we've learned a lot more. I mean, as technology gets better, we can learn more stuff, but also get more confused by more things that are coming out because it's never going to make 100% sense, I don't think, anyway.
Excellent.
Yes.
And so we've got a few more pictures. We've got a few more objects in our solar system. Let's get to those.
Right. So this one came out a couple days ago, I think. And so what are we looking at is we've got, many, many, many different background galaxies, hundreds of them. This very cool spiral galaxy showing its face over here. And then we also have this bright thing here, and it's got the classic 8 diffraction spikes, 6 big ones, 2 little ones. That just has to do with Webb and how it works. And then we've got this ringed planet here. And so this bright thing is not a star. It's actually Neptune's moon Triton.
Oh, wow.
And here is Neptune. Yeah. So we're actually looking at the Neptune system in this image with a bunch of background galaxies as well. So here's how we've seen Neptune so far, right? We have this image from Voyager 2 when it flew by, and we have an image from Hubble in 2021. And finally, now we have Webb from 2022. And we can clearly see not only rings in this image, we have one here, but a thin dust band going through, and these bright little dots, and those are moons. Those are some of Neptune's moons.
Right.
So Neptune in the optical or the visible light is blue due to methane gas. Methane absorbs a lot of the red light and reflects a lot of the blue light. So we get this blue color to Neptune. In Webb, we don't see invisible. So we get this interesting color that they've assigned to it in terms of brightness.
Right.
So here, what we see is, here's Neptune again with Triton, kind of a tighter view zoomed in, and Triton outshines Neptune in terms of Webb's viewing because of what it is made out of, right? So Neptune has a frozen sheet, not Neptune, sorry, Triton has a frozen sheet of condensed nitrogen that is around the surface of the moon. And nitrogen reflects 70%, like especially when it's frozen, it reflects 70% of the sunlight that hits it. So a lot of light gets bounced off of Triton. And it outshines Neptune because of this, but also because Neptune absorbs so much light in that red wavelength, bordering onto infrared, which is what Webb sees. So if it's absorbing all that light, Webb can't see it. Webb sees the light as it bounces off. So Triton appears much brighter than Neptune in the infrared. Also, fun fact I learned today is that Triton orbits backwards around Neptune in a retrograde motion, which is hilarious. I was like, okay, cool.
Well, isn't that indicative that it might be a captured Kuiper Belt object?
Yeah, it might have been captured by Neptune at some point, and so its orbit is different from the rest of the stuff that's going around Neptune, which I thought was very cool, but also...
So maybe at some point in the solar system history, Triton was a dwarf planet.
Yeah, maybe, and it just got scooped up as a moon. I love definitions because why? Space hardly cooperates. But
well, because if you compare Triton with Pluto, they are kind of similar in a lot of ways, right?
They're similar. Pluto's more rocky than we expected it to be. We thought it'd be more icy, but it's got quite a lot of rock, a fair amount of rock in it. Whereas Triton is mostly just icy type moon. But they are both like weird. As soon as you get, I think these are like Newtonian, probably not that, but like past the orbit of Neptune, moving into the Kuiper Belt objects, everything gets a little weird. And we're kind of, it's very odd. There's a lot of different things happening in there, a lot of different materials making their faces shown. So
yeah, very cool. So we've got some more Neptune moons here.
Yeah, so this is just labeling them, which I found helpful because I only know Triton as one of the moons. But we have Galati, Naid, I'm not going to try to pronounce the rest of them, but all these different little dots are actually moons of Neptune. And they were able to capture 7 of them out of the 14 that Neptune has, which is very cool. So we have this new view with all of Neptune's moons and a better look at kind of the whole system as well.
Very cool.
And just to finish off, here is this zoomed in gorgeous picture of Neptune. They think that it is like the brightest regions are like higher altitude regions again. And so they think that they think that there might be a huge storm happening across Neptune because they have these very high altitude clouds right across like the lower equator region. And so not too sure what's happening with that. Hopefully the paper will drop soon / I will find it soon so I can read it.
Well, one of the classic, I mean, we don't know a whole lot about Neptune. As you said, only one spacecraft has ever flown by it, and that was Voyager. And one of the classic things that came out, from that mission was these clouds that weren't visible before from ground-based telescopes that whipped around the planet at incredible speeds, kind of unlike how the big red spot on Jupiter kind of like stays constant, but these clouds on Neptune seem to arise, whip around, and then kind of just dissipate. A lot going on in the atmosphere of Neptune.
There is a lot going on, and it's it's hard to study because it is so far away, right? So like Voyager 2 being the only spacecraft that's flown by it, Hubble has taken a look at it, but as you can see, Hubble gets a pretty good view, but Voyager 2's is just like amazing, probably because it was so close that it was able to get this differentiation of the cloud bands. And so using Webb with an infrared look to get an idea of the cloud structure will help with understanding the storms and the atmosphere of the planet.
Very cool.
Yes, those are all my pictures. Very cool stuff.
Excellent. Well, if you're out there watching on YouTube or on Facebook, drop a comment into the chat. We've got a few more minutes to answer any of your questions. Marley, there is one more big mission that we should mention before we wrap for today, and that's happening on Monday. And we teased a bit about it last show, and that is the DART mission, the Double Asteroid Redirect, that is going to be happening on Monday at about 4:15-ish Pacific time. And you can watch some of the scientists talk about it live. And as the results roll in, what are you looking forward to with this DART mission?
That if it works, I don't know. It's a new type of science, right? Like the kinetic impactor testing has never really been done before, especially out in space, like on a system. So that'll be cool. Yeah. So just like seeing if it works. I also didn't mention last week, but two of the CubeSats that are on board, the Cube satellites, their names are Luke and Leia, which I thought was very fun. So shout out to the Italian Space Agency for keeping it real. Very fun.
Well, yeah, and Andor just dropped yesterday. I don't know if you watched the first episode yet.
Not yet. Don't spoil it.
Drop it in the chat if you've started watching Andor yet or not. I'm going to watch episode 2 tonight. So just as a quick recap, maybe just describe what the Double Asteroid Redirect is doing and what its goals are.
So the goal of the Double Asteroid redirection test is to see if it is possible to move something out of the way using kinetic energy. So what they've done is they've targeted a system, the Dimorphos system. Yes. Because the other one is Didymos. I always mix their names up. But the Dimorphos system, Dimorphos is a large-ish asteroid with a small asteroid moonlet. So that's Didymos that orbits it. And so what they're going to do is try to knock Didymos out of the path of Dimorphos, just kind of, or not out of the path, but knock it onto a new orbit to see if it's possible to change the orbit of something using kinetic energy. That's what that is. It's speeding ahead. Basically, DART, the satellite will just like smack into the surface and try to push it into a new orbit. And it's part of the planetary defense program to see if there is an asteroid that is a threat heading towards Earth, could we just launch something at it and effectively push it out of the way? So that's what they are testing with this. And it's going to be very exciting. They have the 2 CubeSats that will kind of take images as it goes to see what happens. And then also DART itself will send back information up until it collides and destroys itself. So there's never an easy way to say that. So that's what'll be happening on Monday at about 4:15-ish Pacific time. And everything's kind of already been put in process. It's been able to reach the system fine. It's orbiting fine, and the 2 CubeSats have deployed fine. So now it's just waiting for the big event to happen.
Yeah, excellent. Lots of people commenting about all the amazing pictures. Harry, you're a bit late because we actually teased out that, because Harry asked, Pluto is not important enough for picturing. But Marley, as you pointed out at the beginning of the show, it looks like Pluto is going to get an image from JWST soon, right? It's
definitely, the near spec is the spectrometer, or the so it'll definitely get some sort of spectra, but I anticipate an image also, because come on, do it.
Excellent. Well, Marley, happy equinox to you and to everyone out there watching on YouTube and for the first time ever on Facebook. Please join us next time. We're going to be back live here on Facebook and YouTube at 2 p.m. Pacific time on October the 6th. That's going to be our Jupiter Moon Day. We have an event that evening that we're going to be selling tickets for. Go to our website, spacecenter.ca. We're going to have a special guest, the team, one of the members of the team from UBC that discovered a whole bunch of new moons of Jupiter. So that's going to be really exciting. Of course, if you're looking for something to do tonight, we have a movie screening, Star Stuff, a fascinating documentary from Iranian filmmaker Malad Tankshir. It is the Canadian premiere of this wonderful documentary that goes to 3 observatories around the world, talks to the astronomers, and also talks to some of the indigenous communities that live around those very remote observatories. And it is very visual, very poetic, and a wonderful watch. And, it's clear we'll bring out the telescope and look at Jupiter because it is in opposition, which is the closest it's ever been in, what is it, 50 years
50,
or so?
59, I don't know. It's close. It looks good. It's good viewing time. Go check it out.
Very close. And you know what? Even just go to your backyard and look up. Jupiter is going to be very, very bright. Thanks so much, folks. We will see you in 2 weeks.
Bye.